In this video, I'm going to demonstrate how you can carry out forward, backward, and stepwise multiple regression in SPSS. Basically, these procedures are utilized as strategies for identifying significant predictors of some dependent or criterion variable. Um, the strategy is essentially empirically based, and so what can happen, and one limitation of these particular strategies is that a model that you generate through these means may not generalize well to population. So in other words, you may have a model that fits really well to your data but not necessarily generalize. Nevertheless, these are some strategies that people sometimes utilize, or researchers sometimes utilize, um, to identify possible predictors of some outcome measure. So that is the emphasis here. In another video, I illustrate the use of hierarchical multiple regression, and with that, the emphasis is on identifying predictors over a set of models that are entered based on logical or theoretical grounds. So for starters, let's start with forward regression analysis. We'll go to Analyze, Regression, Linear, and basically this data set right here, I've got a set of variables included. I'm going to try to predict international attitudes, or basically attitudes towards internationalism, and I have a set of predictor variables. I'm going to include authoritarianism, social dominance, and whether or not a person holds more economically conservative versus liberal views. So I'm going to include that as a predictor as well. To run the forward regression analysis, I'm going to go to Method, and where it says Enter, I'm just going to hit the little arrow and go down to Forward. On the Statistics button, I'm going to click on it, and I'm going to ask for R-squared change, as well as generally any other things as well. I would typically ask for descriptives, part and partials, collinearity diagnostics, and so forth. I'm just going to keep it simple and just ask for the R-squared change value, because basically what's going to occur is that the program is going to enter in predictors in a series of models, and I want to see how much the R-squared change is. So basically, as we add in predictors, how much additional predictive power do we gain when we do that? So now I'm going to click on Continue, and you'll see under Options, this is um, the decision rules for some of these different procedures. So you can see use probability of F entry at 0.05 and removal at 0.10. These are relevant for some of these different empirically based strategies for entering or removing predictor variables. So at any rate, I'm going to click on, so I'm just going to leave this alone, click on Continue, and then on OK. And so you'll notice for the regression, the method is forward regression, and basically you've got model 1, model 2, and the variables that are entered in those subsequent models. So in model 1, we have economic conservatism as a predictor of internationalist attitudes. So there's economic conservatism as a predictor of internationalism, and basically, for that model, we have our R-square value. So this is the proportion of variation in internationalism accounted for by economic conservatism. So it's 0.215. If you multiply that by 100%, we would say that economic conservatism accounted for about 21.5% of the variation in internationalism. So there's our R-square value right here. So is 0.215. So we also have, our model. This F-test right here is a test of the significance of the set of predictors on the dependent variable. So this is obviously a simple regression, so there's only one predictor here. Then in model 2, you'll see that the R-square value, after we add in SDO, increases. So now we have economic conservatism and SDO as predictors of internationalist attitudes. And so we have, in this case, the R-squared value is 0.282. 0.282. It's very hard to draw like this, but there we are. And we see that that model was statistically significant. So for model 1, the R-squared value was significant. Model 2, R-squared was significant. The R-squared is, again, reflecting the combined set of predictors, the effect of the combined set of predictors on the dependent measure. And then we have the R-squared change value, which is the change from model 1 to model 2 R-squared. So in other words, this is easily computed as taking the R-squared value here and adding this value here, which would get you the 0.282, or just simply the 0.282 minus 0.215. At any rate, it basically gets you the change in R-squared between your two models. So the change in R-squared is 0.068. And over here we have a significance test, testing for whether there's a significant change in R-squared from one model to the next. So we do see that there's a significant change in R-squared by adding in this variable alongside this variable. Notice that there's no model 3 or 4, and that's basically because there would be no significant increment in R-squared from by adding in additional predictor variables. So we had basically going back. Oops. Yeah, so going back, we basically had we'd actually included 3 predictors, so it would only be a model 3 potentially. But at any rate, basically adding in the authoritarianism variable would not have yielded a significant increment in R-squared. So hence the program terminated at that point. When we look down here in the coefficients table, we've got our unstandardized and standardized regression coefficients and t-values for model 1 and model 2. So you can see what's going on right there. So basically with forward regression, it involves a series of steps where you add in predictors across those steps based on empirical criterion. Basically, the idea is that predictors are included when they contribute significantly to the overall model. At the point that the predictors do not, then the algorithm terminates, and the model that you're left with is just a model that's where the R-squared value from that model and the previous R-squared value the change in R-squared had been significant. So that's basically forward regression. And backward regression, what we'll do is we'll click on method and backward. And in this case, we'll leave everything exactly the same. In this case, when we click on OK, you'll notice that the first model incorporates all of the predictors. So in other words, we've got economic conservatism, we've got authoritarianism, and we have SDO, all as predictors of internationalist attitudes. So in this particular case, we can see that as a set, the predictors account for about, you can see with the R-squared value, about 28.9% of the variation. So the R-squared value that we see right here is 0.289. And basically, so this is model 1, and in model 2, we're getting rid of variables that are not contributing to the model. So we're basically pruning at that point. So in this case right here, we can see that we prune out authoritarianism, whereas SDO is still in there. And so in this particular case, we have just economic conservatism and SDO as lone predictors of internationalist attitudes. And you'll notice that in this case, the R-squared value is actually is equal to 0.282, and essentially the change between these two is negligible. So the change in R-squared, basically when you dropped out the authoritarianism variable, we really decreased the predictive power by only 0.6%. So in other words, the change in R squared that we observe right here was negligible, and so you can see the p-value that's given right here. This change is non-significant, and so logically, if we're seeking out the most parsimonious model, the more parsimonious model would be Model 2 as compared to Model 1, because Model 2, we're explaining just about the same amount of variation, that should be a 2 right here, as Model 1. So by eliminating the poor predictor, we still maintain just about the same amount of predictive power. And so you can see that, so again, our R squared for Model 1 was significant, R squared for Model 2 was significant. The change in R squared by dropping out this predictor variable right here was negligible. So then we have down here we've got Model 1, Model 2 with their respective coefficients, and these are interpreted for each model in exactly the same way that you would interpret the coefficients from a forward regression or hierarchical or even a simultaneous entry regression. So that's basically backward regression procedure in a nutshell. Then we have stepwise regression, which is really kind of a hybrid of forward and backward. So in this case right here, we would click on method and stepwise, and just kind of leaving everything exactly the same way. We'll click on OK, and you can see that really in this case the results largely mirrored the forward regression. Basically with backward regression or stepwise regression, what happens is that we enter in predictor variables, and when and sometimes what happens is that when you enter in a predictor variable at a later stage in a later model, the predictors that were entered earlier become non-significant. And so with forward regression, those predictors would remain in the model, whereas in backward regression, what would happen is that those predictors would be, or excuse me, with stepwise regression, those predictors would be eliminated. So literally, you're seeking out only those predictors that would be statistically significant in the final model. In the current case, the stepwise procedure basically mirrored, or the results basically mirrored those results that we saw previously with our forward regression. So basically adding in SDO didn't produce a non-significant economic conservatism variable, so predictor, so it remained in the model. Whereas if we had if this had become non-significant, then perhaps we would have only had the SDO in there. So at any rate, that's basically the forward, backward, and stepwise procedures in a nutshell. And we can mimic these just as easily, by if we go under analyze regression, we could actually run a hierarchical regression and do essentially the same thing. In this case, I could put as what we did right here. I could just put internationalism as a dependent variable, economic conservatism as the lone predictor in step 1, and then STO as an additional predictor in step 2, and click on this right here, and there we go. We end up with well, we ended up with most of the same results, except for the fact that our n was a little bit larger in this case as compared to what we had previously, because there was some missing data on a variable. But had our data set, had we included the same included the same cases for both analyses, they would have yielded exactly the same output. So the long and short of it is that, like I said, these different kinds of stepwise procedures, basically forward, backward, and stepwise regression analyses, are basically they pivot off of an empirical strategy aimed at identifying the predictors or set of predictors that are most significant in explaining variation in a dependent or criterion variable. In forward regression, the strategy is basically to add in additional predictors to a point at which there's really no change in the R square from one model to the next. With backward regression, you're starting with a full complement of predictors and essentially pruning out predictors across a set of models. And then stepwise procedure basically is sort of a hybrid of those two procedures. So at any rate, this was a very short and sweet video. It was not intended to be exhaustive, but this was just sort of a how-to in terms of utilizing these three procedures.